In this video, you will learn how to create a simple state machine that will give you better control over your code, making it easier to implement AI into your games and allow you to automate certain behaviors. Howdy, and welcome to Game Endeavor. State machines are a vital part of coding complex behaviors in your games, such as wall jumping, climbing ladders, and enemy AI. It allows us to organize our code and limit its scope based on its current status. I use them daily in my developer job, and in this tutorial I'll be showing you how I quickly implement a reliable state machine. Let's go ahead and get started. We're going to be creating an abstract state machine, meaning you will never use the script directly. Instead, you will always inherit from it and call the method hooks that we'll provide. The state machine will be a script that will attach to any node, meaning we don't need a dedicated scene for it, just a script. We need to keep track of the state that we're currently in, so I'll create a variable named state. Sometimes it's useful to know what the previous state was as well, so we'll create another variable named previous state. The state machine is going to act as a sort of interface. It's not going to perform any actions on its own. Instead, it's going to check some conditions and then tell its parent what it should be doing. To do this, we're going to need a reference to what we'll be controlling. So I'll create an onReady variable named parent, which will set to the return value of getParent. Every tick, the state machine is going to have two phases. For the first phase, it's going to call the logic required for the state. For example, in a jump state, we would allow the player to move left and right. We would apply gravity, and then we would want move and slide to be called. But if we were in a wall jumping state, then we would not want the player to move horizontally, else they would fall off of the wall. So we're going to create a method that will handle the logic, which we'll name stateLogic. We're going to be calling this method in physics process, so we'll want access to delta. Go ahead and add that as a parameter. This is going to be a virtual method, meaning it's expected that we're going to override this method in the script that inherits from this. So we're not going to create any code for it here. We'll simply close this method with a pass statement. Next, we want to handle the transitions that change our state. This is where we'll determine if we can go from standing to jumping, or jumping to falling. However, you may not want to go from wall jumping to moonwalking, and this method will be how we manage those transitions. So we'll make another method named getTransition. Although not as useful to us here, we're also going to pass in the delta parameter, since we're also going to be calling this in the physics process method. This method will be virtual as well, but we're expecting a return value from it, so for now we'll have it return null. Not only do we want to perform the state logic every tick, but often we will also want to perform some logic once we enter a new state or as we're exiting a state. So to prepare for this, we'll create a couple of methods, the first being enterState. This will take two parameters, the first being newState, which will be the state that we're transitioning into. This is the most common value that you'll be checking for. The second parameter will be oldState, which will be what we're transitioning out of. In this method, it's very common to do things such as setting your animation for the state, or starting tweens and timers. This method is also virtual, so we'll close it with a pass statement. The next method will be exitState, and we'll need the parameters oldState and then newState. And finally, we'll close off this method with a pass statement as well. Now that we have these methods, we need some sort of mechanism for changing our state, so we can ensure that these methods are properly called. So we'll create a method named setState. This will need a parameter of newState, so that it knows what state we're changing into. Since we're keeping track of our previous state, we can update our variables first and then call the enter and exit methods. So we'll set previous state equal to state, and then we'll set state equal to newState. First, we're going to call our exitState method. So we'll make a call to that and give it our previous state as the first parameter, and then newState as the second parameter. However, if our previous state is null, then there is no reason for us to call this method, because there is no state for us to exit from. So we'll add an if condition before this, checking to see if previous state does not equal null. Now that we've exited the state, we want to enter the new state by calling our enterState method. And then we'll pass to it our new state and then previous state parameters. But again, there's no need to call this method if we're not entering a state. So we'll preface this with an if condition checking if newState does not equal null. And that's the mechanism for changing our state. If you want to call this automatically anytime the state variable is set outside of our script, then we can have our state variable use the setState. Keep in mind though that in this script and scripts that inherit from it, we will need to call the setState method directly. Now that we have these methods, we will go ahead and create our physics process method. We're going to check to see if our current state is not equal to null. There's no reason for us to perform state logic or transitions if we have no state. And then, inside of this if condition, we will call our method stateLogic and pass to it the delta parameter. We're going to call getTransition as well, passing to it the delta parameter, but we're going to store its return value in a variable named transition, which will immediately check to see if it is not null. If it's null, then we're going to assume that we shouldn't change our state, otherwise we will need to change it. So we'll call our setState method, passing to it the transition variable. The values that you use for the states are entirely up to you. The only requirement is that they need to be unique in some form or another. You can use enumerators, string constants, and even integers if you really wanted to, but don't be that guy. The thing to keep in mind, however, is that you may need to have a nested inheritance for your state machines. So if you use an enumerator, then you will be incapable of adding more states to the enum. What I'm going to do is set up a dictionary of states that we can append to and use. So I'm going to create a variable named states and initialize it as an empty dictionary. Then I'll create a method named addState, and it will be taking a string value as a parameter. And inside of this method, all I'm going to do is set states, state name, equal to the size of the states dictionary. So the first entry will start at 0, the second entry will be 1, and so on. You shouldn't remove states from this, but you will be able to add to them. There's no real advantage to doing this, I just think it looks cleaner, and it allows you to print out a list of your possible states. Now all you have to do is create a state machine that will inherit this script. Copy over the abstract functions to your new script. Add your states in the ready method, and then you can initialize your state. You will most likely want to set your first state using the callDeferred method. This will set the state during the idle time, which will allow the parent to populate their properties and be ready for manipulation. Because the state machine is a child of the parent, it will load before the parent. To help demonstrate how you would use this state machine in your projects, I have created a simple enemy AI that will stop moving when you're looking at it, but when you turn away from it, then it will chase you. And once it is within attacking range, it will jump at you as an attack. However, it will not attack you if you are looking at it. It will also turn to face you, but only if it is not attacking. Without a state machine, your code would be full of complicated if statements for each of these conditions. And this is a simple AI with only 3 states. But with a state machine, it is far more streamlined, easier to read, and a lot less prone to bugs. I won't go over all of the code right now, because we will cover enemy AI in a future video. But as you can see, we have our state logic method that handles what the parent does. For every state we're applying gravity, then we check to see if we should turn, but only if we're not in the attack state. We chase the player if we're in the chase state, otherwise we stop moving. And then we use apply velocity to actually apply the movement. In the transition method, we use a match statement to check which state we're in, and if our state should change. For example, if we're in a sleep state but we should chase, then we change our state to chase. Or if we're in an attack state, which is a jumping attack, then once we're on the floor, we should set our state back to the sleeping state. And then we have our interstate method, which in this case is primarily used for setting animations. But as you can see, when we enter the attack state, we also call the parent's attack method, which is what causes the sleeping angel to jump towards the player. In future videos, I will be showing you how we can use this state machine to perform wall jumping, enemy AI, and more. So if you're new, then join the sub club to get notified for future videos, and until next time, y'all take it easy.